This is Alex Lawrence Barkley of Sense Media. We're at the inaugural AutoSens conference at Auto World, Brussels, Belgium. I'm here with Jeff VanWashenova of CEVA. Jeff, first of all, welcome to AutoSens.
Oh, thank you.
How are you finding the event?
It's been a great so far. I think there's been a good participation throughout the value chain, anywhere from IP suppliers all the way up to OEM, so been very positive.
Tell me about what you're showing off during the show today.
Okay, well, CEVA's a silicon IP provider, and we've actually created a vision platform which includes the silicon IP, software libraries, and also development tools and environment.
Right, and we've got a demonstration running here. Can you tell me, just walk me through it very quickly? What are we seeing on the screen here?
Yeah, so we've worked with a company called AdasWorks, and AdasWorks is developing autonomous driving software. So it's very important to have low power, low cost solutions in the market today, and CEVA is the platform to deliver those types of solutions. So what we have here is this is actually a FPGA implementation of our XM4 core. We've actually have a set of tools and development software like our CDNN2 software framework, where we have a network generator, which we can take fully trained 32-bit floating point networks and translate that and convert it and optimize it to our core running at 16-bit. So what we have here is a scene segmentation or Freespace Detection demo. So basically we're segmenting the area where the vehicle can drive from the areas that are not safe. So this is very important for autonomous vehicles. So this is actually just demonstrating just the vision system, but in general, throughout automotive, I think it's important to have redundancy of different sensors. So I would say that a vision system is an important part of a larger autonomous vehicle system, which would include LiDAR and RiDAR for redundancy and accuracy. The Freespace Detection demo, which we actually used our CEVA network generator, which is very important in getting very heavy 32-bit floating point networks into 16-bit fixed point networks that are more suited for the embedded environment. So demonstrating this demo, which we use the network generator, but also showing a demo as well on how quickly that can be done for our customers.
Right, so you mentioned there you've got a migration from 32-bit to 16-bit because it's more stable. Can you just quickly explain that?
Yeah, so in the R&D realm within automotive, a lot of companies are developing their neural networks on very large compute platforms. Most of this development is done in 32-bit floating point, which is really good if you have unlimited compute power. But when you want to move to a system for the embedded environment like you do in automotive, it needs to be smaller, it needs to be cost effective, and needs to be efficient. So in moving from 32-bit to 16-bit fixed point, it actually lowers the size of the code that can fit inside the embedded system. So it's more suited for the higher volume applications that you'll get in ADAS in the future. Right,
so it's putting a lot of pressure on making sure the code is extremely efficient, and as a result that's lowering presumably the power consumption demands of the system as well.
Yeah, that's right. So when you're utilizing the CEVA cores, we have a high utilization of the core, much higher than you get in GPU or FPGA systems. So as you move from 32-bit floating point into 16-bit fixed point, it's more apt to higher volume, lower power efficient systems.
Jeff VanWashenova next to me from CEVA. Jeff, thank you very much for your time.
Thank you.